Okay. So, basic concept we have seen, particularly the current, voltage, and that your power, and that power supplied and power absorbed, right. So, we will now come to the basic laws. So, generally your in the electrical circuit analysis, right, the concepts such as current, voltage, and power in an electrical circuit have been we have studied in the chapter 1. Now, in a given circuit, to determine these variables require that we must understand some fundamental laws that given your that govern electric circuit. So, these laws are known as Ohm's law and Kirchhoff's current law and Kirchhoff's voltage law, that is KCL and KVL, and before that Ohm's law. So, these laws actually form the foundation upon which the electric circuit analysis is built. So, in this topic actually in addition to the laws, we will also learn, right, some commonly applied techniques in electrical circuit analysis. This technique actually include the current division, voltage division, combining resistors in series or parallel, and start to delta and delta to star transformation, right. So, in this particularly in that basic laws, we will see that application of these laws and the techniques will be or what we will call restricted to only resistive circuit, and several examples are presented. So, in this case we will present several examples, but as the DC circuit, so we will only consider the resistive part, right. But let us try to understand this. So, first is let us see the Ohm's law. In general actually materials have a characteristic behavior of your resisting the flow of electric charge. If it is resisting the flow of electric charge means it is basically resisting the flow of current, right. So, the physical property or ability to resist current is known as resistance. So, for any material, right, it has some physical property or ability to resist current is known as resistance and is represented by the symbol R, capital R. This is the symbol R. In other words, resistance is the capacity of materials to impede the flow of current, or more specifically the flow of electric charge. So, circuit element used to model this behavior is the resistor. So, this is actually that what you call regarding the resistance. Now, conceptually we can understand the resistance actually of a material if we think about moving electrons that make up electric current interacting with and being resisted by the atomic structure of the material through which they are moving. So, because of the your course of this interaction, some amount of electric energy is converted to thermal energy and dissipated in the form of heat. This effect actually is not desirable, but many useful electrical appliances take advantage of resistance heating, including space heaters, iron stoves and toasters, right. So, this we take that your what you call that your what you call the effect of resistance, right. So, if you see that figure 2.1 to figure 1a, it shows a material with uniform cross section sectional area of A, length is L and resistivity is ohm rho, that is ohm meters, right. So, this is your I need not mark it by reading, it is understandable. This is your what you call uniform cross section is like a cylindrical shape, that all wires it looks like a cylindrical shape, and this length L and cross sectional area of it is A, right. So, it is circular and material with resistivity rho, and this is the symbol of the resistance, and this is the current entering, this is the plus minus, right. So, resistor is a positive, later we will see that resistor earlier we have seen, but again we will see that a resistor is a passive element. So, it absorbs power. So, that is why this is the current, this is a 2 terminal and this is the resistor R, and current is entering into the positive terminal, across the resistor voltage is V. So, resistors actually absorb power, that is why this way we represent, right. So, because it is a passive element, it will absorb power. So, that is why it is, and that is why it is your what you call your plus it is taken and minus it is taken convention wise. But if we reverse the direction also for solving circuit, one can do it, but ultimately we will find resistor actually your what you call that absorbing power, because current enter, that is why this convention is taken, this symbol is for resistor, right. So, we know that from your class 12 physics electricity subject, we know that R is equal to rho into L by A. right. So, that amount of resistance actually depend on the material. So, what type of material you are using, that it depends, like gold, silver, aluminum, copper and other thing, right. So, good conductors such as copper and aluminum have low resistivity. If you have low resistivity, then you have your what you call, you have the low your resistance, right, and hence have small values of resistance. So, they are good choices for wiring, right, your used to conduct electric current. In a circuit diagram, copper or aluminum wiring is not copper or aluminum wiring is not usually modeled as a resistor. If you take a wire, you cannot model it as a resistor, because wire has a very negligible resistance, you can ignore it, right. But resistor actually made of your what you call the carbon and some compound of alloy, right. So, in circuit connection, copper or aluminum is not usually modeled as a resistor. You will take resistance of the wire in the if you take resistance of wire is 0, right. So, the resistance of the wire is so small compared to the resistance of other elements in the circuit that we can neglect the wiring resistance. So, it is so small, it is almost 0, we will neglect it, right. And for and such that our circuit diagram will be simplified. For the purpose of constructing circuits, resistors are usually made from metallic alloys and the carbon compounds, right. So, in the first year when you will do first year lab, there you will see barrel type of rheostat, right. So, the circuit symbol for the resistor is given. This is the circuit symbol for the resistor is given here, and I told you something about this also, why you would make it like this, right. So, and there are some materials of I have brought it for you, that resistivity is for commonly used material like gold, it is resistivity it is ohm meter. So, gold is 2.45 into the minus 8, it is a good conductor, but you cannot use it, because very expensive. Silver also 1.64 into the minus 8 is a good conductor, but silver also expensive, you cannot make it. But copper and aluminum 1.7 into minus 8 is a good conductor. Aluminum also 2.8 into the minus 8, that is also good conductor. Other thing are semiconductor. I have just for comparison purpose, that conductor, semiconductor and your insulator material, just I have given a table. Now, silicon is 6.4 into 10 to the power 2, it is a semiconductor. Carbon also 4.4 into 10 to the power minus 5, it is your semiconductor, and germanium 47 into 10 to the power minus 2, it is a semiconductor, and mica it is 5 into 10 to the power 11. So, insulator, this is all ohm meter, unit is given here, ohm meter, and paper 1 into 10 to the power 10, this is insulator. So, conductor, semiconductor and insulator, and their resistivity, something I have taken, I have kept it here, right. So, now ohm, that GS ohm actually his lifespan was 1787 to 1854. So, here a German physicist actually who established the relationship between the current and voltage for a resistor, right. So, this relationship is known as your Ohm's law. So, Ohm's law is the algebraic relationship between voltage and current for a resistor. So, actually Ohm's law states the voltage V across a resistor is directly proportional to the current I flowing through the resistor. I mean, if you have a resistor and a current is flowing through this resistor, say this current is I, and across the resistor if voltage is V, so V is proportional to I. That is V is equal to R I, that constant of proportionality actually R, that is called resistance. So, that is your V proportional to I, that is this is equation 2.2 for chapter 2, or V is equal to I R, right. So, equation 3, that is 2.3, the mathematical form of Ohm's law. Ohm defined the constant of proportionality for a resistor to be resistance R. The resistance can change if the external or internal conditions of the elements are altered. So, that it can be changed if you internal or external things are of that element altered. For example, if temperature increases, so resistance change, right. If there are changes in the temperature, so R will change. So, R in equation 2.3 is measured in the unit of ohm, designated as ohm, right. So, equation 2.3, that means this equation 2.3, right, we can write that your R is equal to V upon I, right. That means V is volt, I is ampere and R it is ohm. So, 1 ohm is equal to 1 volt per ampere. So, this is understandable, a simple thing, this is understandable to you, right. Now, the polarity of voltage V and the direction of the current I must conform with the passive sign convention as shown in figure 2.1b. 2.1b means this figure, I showed you earlier, this figure 2.1b. I told you that R is a passive element, resistor is a passive element, and current entering into the positive, we have taken plus minus and assuming current entering the positive terminal. So, it absorbs power, and across this the voltage is V is equal to IR. So, that this is that convention, this is the convention, this is figure 2.1b, I told you earlier also, right. So, therefore, your this if current flows from a higher potential to lower potential, right, V is equal to IR, it is true, and if current flows from a lower potential to higher potential, then V is equal to minus R. The meaning is something like this. Let me go to this figure 2.1b, right. So, it is showing current your plus I this way, that is higher potential to here it is mentioned that higher potential to lower potential, right. So, if the current flows from a higher potential to lower potential, V is equal to IR, but if it is current flows from a lower potential to higher potential, V will be is equal to minus IR. That means your let me just for your understanding. So, I mean this is one, but if it happens so, say this is I am making plus, this is minus, this is my resistance R, and if the direction of the current is like this is I, this voltage is V, then V will be equal to minus IR, because current is flowing from lower potential to higher potential, right. So, it will be V is equal to minus IR, but when we will solve the numericals, another thing we will find that actually later we will see that your what you call that resistor is a passive element, finally it will absorb power. If V is equal to minus R, it happens, you will find that I will be negative. So, ultimately V will be equal to IR, because direction will change, right. So, in this case, so that means if direction of the current change, it will be V is equal to minus IR. Later we will see, when we will go for KVL equation, we will see that, right. So, let me clean this one. So, this is clear to you, that which is higher to lower and lower to higher potential, right. So, that is V is equal to minus R. Since the value of R can vary from 0 to infinity, R may be 0 to infinity. So, we must consider the two extreme possible values of R, that is when R is equal to infinity and when R is equal to 0. So, for example, look at this circuit before explanation. Suppose this is a your what you call some electric circuit represented by your just a simple box, right, and this is open. So, that means R is equal to infinity, that means current is 0. So, when R is equal to infinity or R tends to infinity, I is equal to V by R. So, if R tends to infinity, I will be 0. So, it is called, when R tends to infinity means it says it is an open circuit, right, and when R is equal to 0, just connect it like this without no other electrical elements, simply wire. So, approximately we are not considering the resistance of the wire, it is neglected. So, when R is equal to 0, so your I is equal to V by R, right. So, R is equal to 0 means it is a short circuit, it will be huge current will flow, and in that case V is equal to 0. So, for open circuit V is there, but I is 0, right, or when R tends to infinity. But when it is short circuit, when you short it, suppose these two terminals are shorted, so I will be there, because it is a closed path, I will be there, current will be high, but R is equal to 0, but V and at the same time V is equal to 0, because V is equal to IR, if R is equal to 0, then V is equal to 0. So, that is why V is equal to 0, this is short circuit, this is an open circuit. So, that means when R tends to infinity, limit V by R will be 0, right. So, it is an open circuit when I is equal to 0. Similarly, when V is equal to IR, when it is a short circuit, right. So, R tends to 0. So, V is equal to 0, but I is not 0 for short circuit, it will be, it is fault actually, it will carry huge amount of current, and if short circuit happens, your electrical devices or elements will be damaged also, right. So, this is the your two cases for short circuit and open circuit and short circuit. Open circuit means resistance is infinity, short circuit means resistance is 0, right. Now, three resistor, you have to understand each and everything and symbol also. So, a resistor is either, it may be either a fixed resistor or a variable type, right. So, there are three different symbols are shown. This is actually, this is fixed type, this is two terminals are there. So, this is a fixed resistance R, say, right, this is a fixed resistance. Now, in this case, this is a variable resistance. So, when you are cutting an arrow through it, right. So, this is actually variable resistance. So, when you will do first year laboratory, you will see the fixed or variable resistance in the same one terminal will be the one 3 point, if you fixed it on the both end of the resistor, you will find it is a fixed value, but one point it is fixed point, another is a variable point. When you will do first year laboratory, the barrel type of rheostat, you will see this. And third one, this one and wiper is there, this is also variable, but this is a symbol of this potentiometer. Perhaps in physics lab, in your higher secondary you might have seen it, right. This is a potentiometer. So, this is third one is symbol for potentiometer or pot for short, right. So, this is a potentiometer and this is a variable resistor. When you are making an the arrow means this indicates a variable, but this is a fixed one. So, these are the symbols. So, everything is written here. So, not telling it again, right. Now, it is worth mentioning here that all the resistors, all the that here that not all the resistors actually obey Ohm's law, right, because resistance may be non-linear, in that case it does not obey the Ohm's your Ohm's law. So, a resistor that always that obeys Ohm's law is known as a linear resistor. So, I have underlined this one. So, a resistor that obeys Ohm's law is known as a linear resistor. So, a linear resistor has a constant resistance and its current voltage characteristic is linear, right, as shown in, and it is passing through the origin. If you see this is a linear resistor characteristic, its slope is R, it is passing through the origin. So, this follows Ohm's law, right, because it is a linear characteristic. But if you see, but this characteristic V by I, it is not a straight line, it is something like a curvilinear, right. So, resistor that does not obey Ohm's law is known as non-linear resistor. So, resistance of a non-linear resistor actually varies with current, and typical current voltage characteristic is, this is the typical current voltage characteristic. For example, your light bulb and diode are the examples of devices with non-linear resistance. So, I mean any devices obeys it obeys your Ohm's law, that is a resistor, that is called a linear resistor. If it is not, that is non-linear resistor, simple thing, right. So, this is the IV characteristic of a linear resistor, the first one, IV characteristic of a non-linear resistor, right. Now, in a circuit analysis, we always represent one thing, that is reciprocal of resistance R, that means is known as conductance. So, that means reciprocal of resistance we define as a conductance, right. For example, G is equal to 1 upon R, right. R is, you know that V is equal to IR, right, V is equal to IR, then 1 upon R is equal to I by V. So, that is why G is equal to I by V, right. So, the conductance G actually is a measure of how well an element will conduct current, this is actually the idea. So, conductance G is a measure of how well an element will conduct your current. So, the unit of conductance is mho or Siemens. So, either actually ohm is the unit of resistance. So, it is reciprocal of that, is why it has been mho, or symbol is also just opposite, right, or Siemens, in short it is S, that is the your unit of the conductance. So, 1 Siemens is equal to 1 mho is equal to 1 ampere per volt, because this is a conductance, see I is the ampere, V is the volt, so ampere per volt. So, 1 Siemens is equal to 1 mho is equal to 1 ampere per volt. This starting, I have started this thing from the very beginning, such that nothing will be left out, hopefully, right. So, thus conductance is the ability of an element to conduct electric current. So, this is that is why I have underlined here, the conductance is the ability of an element your what you call to conduct electric current. Now, equation 7, right, from equation 2.7, this equation I is equal to G B from this equation, right. So, from this equation actually I is equal to conductance into voltage G B. Now, the power dissipated by a resistor can be expressed as P is equal to V I, right. I am not writing by pen here, it is understandable. P is equal to V I and V is equal to I R. So, here I have put V is equal to I R, that means it is I square R, right, is equal to V square upon R, because I is equal to V by R. This one if I write for you, just hold on. So, this is actually I square R. So, I is equal to also we can write no, I is equal to V by R, that means V square by R square into R, that is equal to this one V square by R, right. So, I is equal to your what you call V square I square R is equal to V square by R. So, let me remove this one, clean this one, right. So, this is that means P, that means R is always positive and it is V square. So, power loss across resistor is always positive, it absorbs power, right. Very simple thing, but we have to try to understand this, right. So, P is equal to V I, a resistor is a passive element, it absorbs power and R is always positive, for any circuit you take R is positive and it is V square, whatever may be the V plus or minus, square means always positive. So, P is equal to V square by R is equal, always it is positive, or I square R always positive, that means it absorbs power. Similarly, also just other way you can write P is equal to V I. Now, it is V, but in terms of conductance I is equal to G into V, that is V square G, right, or you can make it is I square G, because V is equal to your what you call your I is equal to G V, right, I is equal to G V. So, V is equal I is equal to G V. So, V is equal to I by G. If you substitute here V is equal to your I by G, I am making it for you just one line. So, if it is V is equal to your what you call, just 1 minute, sorry, this is I is equal to your G into your V, therefore, V is equal to your I by G. So, if you substitute here V is equal to I by G, so it is I square by G square into G, that is your I square by G. So, this is what you have got, right. So, this is I square by G. So, now let me clean it, right. So, here also it is V square I square, I mean G is again positive, it is reciprocal of resistance. So, conductance is always positive, it is V square or I square, whatever may be the positive or negative value V I does not matter, this P is always positive, right. That means it shows that your what power dissipated resistor, your what you call it actually it absorb power, right, resistor absorb power. So, power resistor is a nonlinear function of the either current or voltage, it is a parabolic type, P is equal to I square R is equal to V square by R, or P is equal to V square G or I square by G, it is a parabolic type of function, right. So, its graph will be either this side you plot I or V, this is power, it is a parabolic function, just I have drawn it, right. So, since resistance R and conductance G are just what we told that it is positive, right, quantities, the power dissipated in a resistor is always positive, I told you. Thus, a resistor always your absorb power from the circuit, it absorb, right. This confirms the idea that a resistor is a passive element and it is incapable of generating energy. This is very important for you. When you listen this video, right, just see that what we are discussing, right. Now, up to this your Ohm's law and this thing, let us come now to a small example, like right, an electric heater draws 4 ampere and at 240 volt. So, find its resistance. So, we know R is equal to V is equal to I R. So, R is equal to V by I, V is equal to 240 and I is equal to 4. So, 60 ohm the resistance, right. Another small example, in each circuit in figure 2.6, right. So, this is 3 circuits are there, the value of either V or I is not known, right. We have to determine the the values of V and I, B the power dissipated in each resistor. So, you have to find out V or I, right, whatever it is, known or unknown quantities you have to find out. Now, look at this circuit, is a current source 1 ampere, right, and this is your this current is entering the positive terminal. So, V is equal to IR. So, I is 1 ampere and R is equal to 8 ohm. So, it will be V is equal to 8 volt, and it is your current is entering into the positive terminal, right, that is flowing from higher potential to lower potential. So, it will be positive. So, V is equal to IR. So, it is 1 into 8. So, V is equal to 1 into 8 volt. Now, second case is, it is, I hope I am not marking it by pen, I think it is simple thing. So, it is understandable to you, right. This 1 ampere means this current is this 1 ampere flowing through the circuit. I mean, okay, just let me make it one thing for you. This I is equal to 1 ampere. So, the current is flowing like this, this 1 ampere current is flowing like this. This is actually showing it, this I. So, this I is equal to 1 ampere, this is what is shown here, right. So, let me clean it. Similarly, just hold on. Similarly, this is mho. This is actually, this value is G is given. This is 0.1 mho. G is given. Conductance is given, right. So, this is actually G is equal to 0.1 mho. Conductance is given of this circuit, right. So, in this case, voltage is given your 100 volt. That is 100 volt. So, you have to find out that what is the current. So, just let me clean this one, right. So, in this case, just hold on, in this case your I is equal to, actually we know this thing, I is equal to GV, right, I is equal to G into V. So, it is G is 0.1 and it is 100. So, I is equal to 10 ampere, right. So, it is I is equal to GV. Now, another thing is there actually your what you call, this is 50 volt and this is 5 ohm resistor, but look at that, this current actually flowing, this means current entering into the plus terminal. Later you will find these things will be easier when you will come to the KVL equation, but right from the beginning that current is entering into the positive, that means current is flowing from your higher potential, this thing higher potential to lower potential, right. So, in this case, if you come to this, that means the direction of your voltage rise. So, 25 resistor and the direction of the voltage rise across the resistor. So, I is equal to minus 50 by 25 is equal to minus 2 ampere, right. So, because this is in the direction of your what you call in the voltage rise. So, that is why the negative sign has come. So, that is why it is your I is equal to minus 50 by 25, that is minus 2 your ampere, right. So, this is actually voltage source, right. This is not a resistor, this is a voltage source. So, it is from the voltage, from the higher what you call in the direction of the voltage rise, because it will encounter plus first. When you see KVL thing, at that time things will be easier. So, this is your what you call minus 2 ampere. Now, last B part is your part B, this thing, the power dissipated in each resistor. Here we have seen the current is 1 ampere and it is your what you call R is equal to 8 ohm. So, in the first case, that is V square by R, that is power absorbed by the resistor 8 ohm. So, bracket I am writing power, this 8 ohm means power absorbed in the 8 ohm resistor, V square by R. So, V square actually V is 8, we have computed, divided by R is 8 ohm. So, it is equal to the same thing I square R. So, I is 1 square R into 8, actually it is 8 watt. It is also 64 by 8 watt, I square also 1 square into 8. So, it is 8 watt. So, it is understandable. Similarly, that second circuit, that there G is your 0.1 ohm, this G is actually 0.1 mho and voltage is 100 volt. So, in this case you can see that power basically it is a resistor say. So, it is your what will be the power absorbed. So, I square by G. So, I is 10 ampere. So, 10 square by G is 0.1. So, it is equal to same thing V square G is equal to V is 100 volt and G is 100 square into G is 0.1, ultimately it will become 1000 watt, right. Similarly, pure 25 ohm resistor, that is this circuit 25 ohm resistor, right, whatever may be the current, it does not matter, right. So, it is V square by R is equal to 50 square by 25 and is equal to also I square R, I is equal to minus 2 square into 25. So, ultimately 100 watt. I told you that for whatever may be the direction of the current or the polarity of the voltage plus minus, that power your absorbed by the resistor, resistor absorbed power, its sign will be always positive, right. So, in this, so all these cases you can see it is 8 watt, 1000 watt or 100 watt, all the cases resistor actually absorbing power, right. This is another small thing, that figure 2.7. So, a simple circuit, determine the current I, the conductance G and the power P. So, it is 30 volt source and here one resistor is there and it is 5 ohm resistance and current flowing through this your is I, right. So, in this case voltage across in this case there is no other element here, right, no other element. So, this is 30 volt, that means just for your understanding only, this voltage is 30 volt. So, this is plus minus means this is plus minus. So, this voltage is up. So, whatever plus minus means this is also plus minus. So, this 30 volt means it same voltage will be impressed across this your resistor, that means my V will be is equal to your 30 volt, right. So, same voltage. So, understandable, it is very simple thing, this is plus minus, this is plus minus. So, there is no other element here. So, plus minus, and so whatever voltage is here, same voltage is here because no other element. So, there is no voltage drop, later we will see this. So, V will be equal to 30 volt. So, let me clean this one, right. So, then what will be the current then? So, current will be I is equal to V by R is equal to 30 by 5 is equal to 6 ampere. So, conductance is G is equal to 1 upon R. So, 1 by 5. So, 0.2 mho because reciprocal of R. So, power is equal to V into I is equal to 30 into 6. So, 180 watt, this way you can calculate, or P is equal to I square R, that is 6 square, I is 6 ampere, we have calculated this 6 ampere, 6 square into 5. So, 180 watt, or P is equal to your V square G, that is your 30, V is 30 volt. So, 30 square into 0.2, that is also 180 watt. The way you want you can compute the your power, but is a resistor. So, it will be power absorbed. So, all these cases sign is positive. Thank you very much, we will be back.